Welcome back. Here is an example of how you would find A inverse if it exists. A is given here. So remember the previous theorem? Build a partition matrix or an augmented matrix with the right hand side completely of the identity. We are 4 by 4, so consider the partitioned matrix A and identity 4 by 4 on the right hand side. Now you are going to do reduced row operations on the entire partitioned matrix so that A is brought to its reduced row operations. That's the process. I have a 1 here, that's good. I want to get a 0 here. Okay. To get a 0 here, negative 1 times row 1 added to row 3. Whatever you do here, you must do throughout, including the right hand side, okay? Including the right hand side. So let's see what happens. I get a 0 here and I get this phenomenon here, okay? So let's go back. Negative 1 times row 1 plus row 3. Negative 1 times 1, negative 1 plus 2 is 1. So that's 1. Negative 2 plus 1, that should be negative 1. That's negative 1. Negative 1 plus negative 2, that should be negative 3. That's negative 3. Negative 1 plus 0, that should be negative 1. Negative 1 times 0, nothing, no change anywhere else. No change anywhere else. So we got zeros below. Now notice I want a 1 here. I could divide by negative 2 or I could interchange row 2 and row 3. I interchange row 2 and row 3 throughout. So 1 negative 3 and negative 1 0 1, you see that row comes up and the second row goes down. Negative 2 0 0 0 1 0 0. All right. Now you want a 0 here and a 0 here. 2 times row 2 plus row 3. Negative 3 times row 2 plus row 4. Okay, so it gets 0 0 here. Let's look at row 3. 2 times this plus 0, so that's negative 2. 2 times this, that's negative 6 plus 0. 2 times this, negative 2 plus 0. 2 times 0, no change. 2 times 1, 2 plus 0. 2 times 0, 0, no change. So that's your new. Now I want to get a 1 over here. Okay. That's a 5, so interchange is not very useful. Let me try dividing row 3 by negative 2. Divide row 3 by negative 2. Negative 2 over negative 2, 1. Negative 6 over negative 2, positive 3. Negative 2 over negative 2, 1. 1 over negative 2, negative half. 2 over negative 2, negative 1. Everybody else is the same. You got a 1 here, you want a 0 here. 5 times row 3 plus row 4, that's your new row 4. So below 1, you have a 0 by design. 5 times 3, 15 plus 10, sorry, negative 5 times 3, negative 15 plus 10, negative 5. Negative 5 times 1, negative 5 plus 3, negative 2. Negative 5 times half, negative half, positive 5 halves plus 0, positive 5 halves. Negative 5 times negative 1, positive 5 plus 3. Negative 5 times 0, no change. All right. You got 0 here. You want 1 here. You can divide by negative 5. Row 4 by negative 5. You got a 1. Sorry. And you get negative 2 over negative 5 is 2. Negative 2 over negative 5. 5 halves over negative 5. 2 over negative 5. 1 over negative 5. Check my work. All right. This is row echelon form. You want reduced row echelon form. Start with the last column. Okay. We need continue row operations to get the reduced row echelon form. Start with the last leading one. Okay. I have 3 here, negative 3 here, 1 here. I hope you believe my calculations. I get zeros above. I don't want to go back and forth too much. Check for yourself. You get zeros above. No change here because these are zeros. Here, a lot of change happens. Make sure you get these numbers. Now, you got zeros here. Now you want zeros here. Row 3 plus row 2. Negative 2 times row 3 plus row 1. So I got zeros here and a lot of changes here. Again, check my work. Okay, all we are doing is the row operation. Lastly, I want a 0 here. I get 0 there and some numbers here. I got identity matrix. That's good. So A is invertible. Its inverse is this. That's how you find the inverse. A inverse is what happens to your identity matrix when you apply the same operations, row operations on A to get it to identity. Notice, by now you know, reduced row echelon form need not always be identity. Okay. By the way, you may verify that this times A is identity both direction. Okay. An n by n matrix A is singular if and only if A is row equivalent to a matrix B that has a row of zeros. Suppose I do row operations and end up with a row of zeros. Well, there's no way I can get identity. So it should be singular. Okay. So let's prove it's an if and only if statement. Suppose A is row equivalent to a matrix B that has row consisting entirely of zeros. Since B has a row consisting entirely of zeros, B is singular. Notice B is reduced row echelon form and it has a row consisting entirely of zeros. Anyway, any matrix that has a row consisting entirely of zeros is singular. It doesn't have an inverse. B is obtained from A by multiplying bunch of elementary matrices on the left. All of these guys are non-singular. If A were also non-singular, then the product would be non-singular. That's a contradiction, right? So, B is singular, therefore A has to be singular. If A is non-singular, we hit a contradiction, therefore A has to be singular. Okay. Conversely, what is converse? Assume A is singular. You want to show that when you do row operations, B should have a row of zeros. Suppose A is singular. Then A cannot be row equivalent to identity. Okay, it is, if it were equivalent to identity, then A would be non-singular, but our assumption is A is singular. Since A is row equivalent to a matrix B and B is in reduced row echelon form, B is not identity. B must have a row of zeros. An important remark, given a square matrix A, we investigate its reduced row echelon form B. Okay. If the reduced row echelon form B has zeros, one row entirely of zeros, then A has to be singular. Its inverse does not exist. On the other hand, if B that's the reduced row echelon form of A is identity, then A is non-singular. Its inverse can be found. Here is an example. Let's look at this 3 by 3 matrix. Identify A inverse if it exists. What do we do? Same story. To find A inverse, write A and identity. Do row operations on the left for the reduced row echelon form. Okay, I have a 2 here. I want a 1. Interchange row 1 and row 2. I brought row 1 up, row 2 down. Okay. Now I want a 0 here and a 0 here. So negative 2 times row 1 plus row 2. And negative 1 times row 1 plus row 3. Okay, you do this business throughout. Okay, assuming we get the same result. So notice I got zeros below. Now I have negative 7 here. I want a 1 here. So divide row 2 by negative 7 or multiply by negative 1, 7. You got a 1 here, no problem. Okay, things changed. Sorry. Now I want a 0 below. 7 times row 2 plus row 3. I got a 0 below. The same business gets me 0 here as well. These things changed. But I have a row of zeros. I cannot proceed further. I will never get an identity because I cannot divide by 0. I cannot get a 1 here. One row of this row echelon form is full of zeros. So A is singular, that is I cannot proceed further. Inverse does not exist. Okay? No matter how plausible this looks, I have zeros here. I cannot proceed. So inverse does not exist. So to repeat, for inverse to exist, I need ones throughout. Okay? I need to actually get identity matrix in the row reduced row echelon form. What is an application of A inverse? Suppose A is non-singular. Can I solve for this? Well, how do you solve in linear, in middle school? Divide both sides by A to solve for x. What is the meaning of division? It means multiply by A inverse. So I have to multiply on the left by A inverse. Multiply on the left by inverse, left by inverse. A inverse A cancel. You have x on the left, right hand side is A inverse B. So which brings us to a theorem. If A and B are n by n matrices such that AB is identity, then BA also has to be identity. Now that's tricky. All you're saying is I'm multiplying in this order. Turns out the reverse order also works. That is, B has to be A inverse. Suppose AB is identity. Assume A is singular. Sorry. If it is singular, you will have row operations on A and you land with a row of zeros. C, that is the row echelon form or whatever equivalent, you multiplied a bunch of elementary matrices to A and you got C to have a row of zeros. Now if I multiply on the right by B, all of this right by B, remember AB is identity, CB is equivalent to identity, C has a row of zeros, which means AB also has a row of zeros, which is not possible because AB is identity. So we have a contradiction here. What was the contradiction? Assume A is singular. We cannot have